up, dudes? How you doing? I'll be honest with you. I just wanted to let you know I'm not really prepared for class. I actually kind of wanted to try to teach you guys something a little bit different, a little bit new, and it's actually not math. Not actually specifically math. It's science. But you use math for science, so it's, in a way I am teaching you guys math. I want to show you guys something really quickly. It's a trick, and I think it'll be really impressive. Can you guys see this thing right here? What is it? What does it look like? I called the company and I ordered it. I'll give you a hint. If I had 2 of them, which I do, I could be really cool. Just be like, "Sup, dudes?" Yeah, exactly. They look like a glass popper. I don't know what a glass popper is. Anyway, it's a piece of a lens for sunglasses. We cool? In fact, these are polarized sunglasses. Have you ever heard of polarized sunglasses? Yes, you have. Okay, awesome, awesome. So let me show you guys something. I want to show you guys something. All I'm going to do is I'm going to take this polarized sunglass. Now, here's the problem that I've had is you guys know that I work off of a piece of glass, right? There's a big piece of glass in front of me and I write on it. That's kind of how I teach my classes, and some of you guys have been like, wow, that's really cool. But I just wanted to show this to you really quickly is I'm just going to hold up this piece of sunglasses over to the camera. I want you to take a look at something, okay? All right. So can you see my reflection of me holding the piece of sunglasses up to the camera? Can you guys see that? In fact, actually, where's my tape? I'm gonna tape this thing to it. But I want to show you guys something. All I'm gonna do is I'm gonna turn this piece of glass. Actually, it's not even a piece of glass, it's a piece of plastic. All I'm going to do is I'm going to turn this piece of plastic and we'll see what happens. Okay? Now I'm going to turn it 90 degrees. I'm going to turn it a little bit. Hopefully my hand doesn't get in the way. I want you guys to look at something. Watch. What did you notice? What's going on there? It's getting darker. What is getting darker? Is everything getting darker? The world is getting dark? Everything is getting darker? No, just the reflection for the screen. What do you think? Because what's crazy is that light behind there. Did you see that light? Here, I'll turn it again. Hold on 1 second. That light in the background, that's an open window that's reflecting off the glass. That's not getting darker. My face isn't getting darker. See? Just the computer screen. Why does that happen? Oh, I'm glad you asked, Erica. Well, because of this idea called polarized lenses. Let me show you what 2 polarized lenses look like. 1 second, let me just fix it so I can show you that it's real cool. Okay, ready? Alright, here. All I have is now I have 2 of these guys, right? Can you see through these? Let me put this right here. What's up, dudes? Oh, whoops. I guess you can't see through. Let's see. It's got too much of a reflection. Let's see. Let's turn on the lights. Maybe that might work. Alright. No, it's too hard to show you. It's too hard to show you on the computer screen. But I'll tell you why that happens. Okay? And this will be our physics lesson / math lesson for today. Oops, I mean math lesson, because technically I'm not your physics teacher, I'm your math teacher. So let me just cancel out the glare out of that computer screen, because that's what I was supposed to do anyway. Alright, I got it. Alright, let me just tape it up there. I want to show you guys what's going on. So this is without the lens on top. And then I'm just going to take some tape. So I can get my tape to come off. 1 second. There we go. Just throw that piece away. Get this piece right here. Okay, I'm going to describe for you what happens, what's going on, because I think it's crazy. Let me just put this lens right up there. See? There it is right now, and I'm going to kill the light right there. There's also this green thing over here. There's a green light on there, so I'm going to try to kill that out too. There we go. Just put the tape up there. Hopefully that tape will hold. It's kind of hot, so it'll probably melt a little bit, the tape. Maybe just put more tape up there. Alright. Okay, there we go. Let me grab a marker. Where's my black marker? I don't have a black marker. I guess I'll have to use a different marker. Oh, oops. It's alright. Alright, I'll fix it later. Okay. So check this out. Why does that happen? I'm going to describe this to you really quickly. So to be honest with you, this is not a physics class, this is a math class. But here's what's going on. Light waves, you've seen actually come like this, right? We call those sine waves. I don't know if you learned that in geometry or maybe even Algebra 1. But have you seen a wave that looks kind of like that? Goes up and down. Yeah, I've seen waves that go like that. Alright, but light isn't actually all going up and down. Part of it's going side to side as well. So if I could draw in and out of this board, I guess it would kind of look like this. That looks terrible, huh? 1 second. Can you imagine that light is actually not only going up and down like this, it's going up and down like that, but it's also going side to side like this. That's the way light is. They call it non-polarized light. So actually light actually comes to you kind of in a circle, I guess. Is one way you can kind of think about it. Does that make sense to you? Now, what's really interesting, and you should try this out next time you guys go down to the glasses shop, or if any of your parents have polarized sunglasses, go down to the ocean, all right? Go pick up yourself a pair of cheap polarized sunglasses and go down to the ocean. And what happens is, when the light bounces off a large horizontal surface, like let's say the ocean, okay? All the light that comes in this way, like comes in up and down like this, gets scattered off someplace like that, okay? And then the light that's coming in, think of it as in and out of this board, like this, hits the thing and actually gets reflected back into your eyes. So all of this reflection that we see, I can say that, you know how I told you that light isn't only polarized in one direction, it doesn't only go up and down or side to side, it actually goes both. Well, I can tell you that reflections bouncing off horizontal surfaces definitely are going side to side, because the ones that go up and down got killed. Can you guys agree with me on that? All right, all right. So all the glare that I see when I'm out in the ocean, or when I'm on a long road, because it's all a big horizontal road, all this glare that I see that bounces into my eyes is all, is all polarized this way. What I mean by polarized is all of the vertical part got killed, only the horizontal part is coming into my eyes. So imagine this now, okay, ready? We're doing a different scenario. Imagine you are playing Frisbee. You guys ever play Frisbee? You guys throw the Frisbee like that? Yes, I played Frisbee. No, I haven't. Talk to me. All right. Imagine you're playing Frisbee and you throw the Frisbee at a white picket fence. The white picket fence goes up and down like this. Okay? So you're throwing the Frisbee and you throw it at a white picket fence. Is the Frisbee going to go through? Could the Frisbee go through? No, exactly. But let's say instead it's a weird fence where they actually have a fence where or maybe, like where they have like cattle or something, and they have like the fence that looks like this. They're horizontal lines. Let's say they're horizontal bars on this fence. Okay? Will the Frisbee go through that one? Yeah. So here's what they do. Here's the trick that we use to block out all of this. Here's the trick that we use to block out all of this horizontally polarized light. Is the polarized lenses actually have microscopic lines on them that are vertical. And what that's doing is it's cutting out all of this horizontal light. Now only the horizontal light gets cut out, because the light that's going vertical, I mean, imagine if you, instead of throwing a Frisbee like this, you throw a Frisbee like this. Like, I think that's called a hammer throw, where you basically throw it over your head. So the thing is going like that. That will go through the fence. Not the horizontal Frisbee, though, the regular one. That will get stopped by the fence. So that's what's happening. And apparently, the computer screens are all polarized screens. So I know that the light that is coming out of a computer screen is polarized like this. So all I got to do is turn the thing 90 degrees, and it will cut out all of all I got to do is turn it 90 degrees, and it will cut out all of the light coming from the computer screen. Whereas if I turn it 90 degrees again, it will add back. It will let all that light through, because what I'm doing is I'm turning the fence to be like this instead of this, and maybe the light from the computer screen will be able to get through then. Does that make sense? So I'll show you one more time, and then we got to get started with class. I apologize for doing this little detour, but I thought it was interesting because I got this stuff in the mail today, and I called a glasses shop over in California, and I told them, hey, I'm doing this project where I'm using this big piece of glass, but I'm having a problem with reflection. I think, as a science teacher, this is what I teach my students, is that I can use polarized light or polarized lenses to that. Can you send me some samples of your polarized lenses? So this company called Young's Optics sent me like these samples, these little things that they give to doctors, So I tape one to my computer screen and watch what happens. Like I said. Alright, wait 1 second. Oh man, this tape is not the right tape to use. It is gross. Alright. Okay. Here's a lens. Now watch the computer monitor. So watch. It's dead now because it's blocking out all the light from the computer monitor. But if I turn it 90 degrees, okay, now you can see all the light from the computer monitor. And again, I turn it 90 degrees. Let's just turn it like this. and it kills all the light coming from the computer monitor. By the way, that green light is the green light from my computer screen. Apparently, that's, Mac is saying, your camera is on. What do you guys think? Is that pretty cool? Alright. So, what I'm going to do is I'm going to tape this thing back up to the computer screen using my junk tape. It's all sticky and gross. Anyway, whatever. I'm going to tape this thing back onto the computer screen so I can cut out all of that extra glare. Let me just make sure I'm doing the right... There we go. That should be the good orientation. I'm going to cut out all that extra glare so that way you guys can see the computer screen without having to really worry about the glare. And then I'll get this class started. But I wanted to show you the technology that I'm using. And I'm not really using like super high-tech stuff. I'm literally taping a sunglass lens to my in front of my camera on my computer. So it looks all ghetto, but it works. It works perfectly fine. So now I cut out all of that stuff. Anyway, I don't know if you're interested in that, but I am. So deal with it, because Mr. Dallday's a nerd. Alright. Here's what I'm going to do. Some of you have called me up. Actually, so are we good? You guys good? You guys happy with my lesson? I'm sorry that I detoured from math specifically, but I figured we're going to cover something brand new. I mean, we're not covering something brand new, but I just figured I wanted to kind of show you guys something that I thought was interesting. So, here's what I want you to do, all right? Just to kind of like solidify the lesson that I was teaching you. Go to a sunglasses shop and ask them if you can go and see a polarized sunglasses. Just say, hey, can I see some of your glasses that are polarized lenses? You can buy them for cheap nowadays. They used to be really expensive. They used to be like $60. Now I think you can get them at Ross's for like $5. Anyway, put the sunglasses on, okay, and look very carefully at the glass countertop. They usually sell the sunglasses in a glass case. So look at the glass countertop. And you'll still be able to see the glass countertop, but what you won't see is all the glare. Take your glasses off, put them back on, take them off, put them back on. You try to make sure you can distinguish the two. We cool with that? You guys understand that part? This isn't a homework assignment. This is a, hey, let's be curious about life assignment. How's that? All right. Then the second thing I want you to do is after you put the sunglasses on, you can really pick out the glare. You understand, okay, this is what the glare is, this is what the sunglasses are cutting out. Turn your head 90 degrees. Just kind of do one of these. And what you'll find is all of that glare will come right back. Because remember, the glasses are polarized in one direction, but if you turn your head 90 degrees, they will no longer be polarized in the correct direction to cut out all of that horizontal light. Anyway, I think it's interesting. Let's figure out what you're doing and where we're at. All right, here's what my thoughts are for math. We're going to get finished. We're actually going to, I only got like 20 more minutes, and I apologize. I've been going so long talking about something divergent. But I thought it was interesting to you. I want to get you guys, your brains woken up for this week, and I want to start motivating you guys to like learn this math, because all of this math that I'm teaching is very dependent on if you want to actually like explore the universe and do stuff like I was just showing you, which I think is cool. And I think it's worth pursuing. I feel like I've been tutoring some of you, Joy and Erica. You've been calling me up, and I feel like I haven't gone over, I might have even skipped some sections. And I feel like, Erica, you've kind of been the catalyst for that. So everyone applaud Erica or say thank you to Erica, because she's kind of pointed out to me that I might have skipped a very important piece that I want to go back to. And so what I'm going to do is I'm going to extend your homework on that one, and I'm going to totally let you guys turn in that late work assignment. But I want to go back to make sure I lecture on completing the square, because I think I missed out on doing that. So, everyone say thank you to Erica because basically I'm going to be giving you guys a freebie for your assignments. I'm going to push something back, and because of that, or because of the tutoring, because she said I needed help, that came about. So the reason why I'm saying this is not to point out Erica and say, Erica, you needed tutoring. Ha, you're not as smart as everyone else who doesn't need tutoring. I think actually everyone needs tutoring. Erica was maybe just brave enough. So kudos to you and Joy for asking for help. Because without that, I would have not known. I would have just kept going and just been oblivious to what I was supposed to be like, you guys don't understand. I don't care. It's not that I don't care. It's just I didn't know. So let me figure out what I want you guys to cover. And I think that maybe what I missed out was on functions 4. I might have not covered all that I wanted to. And I think that it's really important. So I'm actually going to spend today on functions 4. I'm going to take all those due dates and put them back, or push them all back to like this week. Because functions 4 was due, when was it due? It was due like, hold on 1 second. It was due last week. So what I'm going to do is I'm going to push that all back to be due this week. Does that sound fair? Yeah. So if you guys, and if you guys feel like I'm going too fast, you have to let me know, because somebody asked me. They said, "Why are you lecturing on function 7 when we're only on functions 4 that was due?" This was last week. They were asking, "Why are you lecturing on function 7 already?" And the reason being is because my goal is to try to get ahead. I hate it when teachers lecture on something and say, "Okay, it's due tomorrow. Have fun." You know what I mean? That's like that puts all this pressure on you. So what I'm trying to do is I'm trying to get ahead and lecture ahead of time, and that way it gives you a good solid 2 weeks or a week and a half or whatever, at least a week, to really kind of work on this and build your skills. That's my goal. That might not always be the best, and apparently it went too fast. So what I'm going to do is I'm going to take a step back and go back to functions 4. I'll probably cover it pretty quickly, but I need you guys to let me know if you guys are confused. Because if not, I won't. If not, I won't slow down, and that makes me feel like I'd be a bad teacher. I don't think I am. I think I'm a very understanding teacher, but I don't want you guys to feel like I just disregard how you guys feel because I'm going to go as fast as I want, whatever. 1 second. I'm sorry, my computer's taking a little bit of time. There we go. We're uploading this thing. All right. So that's my idea that I have with you. Are we cool with graphing this stuff? I showed Joy how to graph this stuff, and she actually found this was really easy. Are you guys cool with that? Yeah. Okay. All right. So it seems that you guys are all happy with graphing this stuff. I'm just gonna tell you what I think this graph is going to look like, and we can check it out on Desmos. In fact, I don't know if I'll do that in class, but anyway, if I got f of x equals negative 1/2 x minus 2 x minus 8, all right. What I look at is this. This is put in a form that is called, actually, I think that the graph they gave me is f of x equals negative 1/2 x squared plus 5x minus 8, all right? And then if you were to use, oh man, you can't see that, I'm sorry. Just kind of do these, and then go over here and say f of x is equal to negative 1/2 x squared plus 5x minus 8. But they said these are equivalent, and I'm not going to go through how to factor this, because I mean I feel like it's somewhat beneath you. All right, yes, I'll definitely go to page 5 and 7. Let's hit that. But yeah. See, that's the thing. That is my point. Is when you ask a question, and Erica, see, I'm so glad you feel that way, because when you ask this question, you're thinking I'm the only one who doesn't understand this, and that's not true. That's not true at all. Apparently, Lena had the same problem, and Elijah was like, "Dude, I don't get it either. I just didn't ask because he said that. Oh, you guys should know this stuff." And Erica's like, "Oh man, I thought I was an idiot. No, that's not true. That is not true. You guys are brilliant, and I'm so proud of you guys for being brave enough to ask. Please continue to ask and continue to throw that out there and say, I don't get it. I'm raising my hand. The whole point of me being a teacher is not to get through the curriculum. It's to help you out. I'm so excited about it. I'm spinning on the chalkboard. Anyway, 1/2 x squared plus 5x minus 8. If I were to graph this, and by the way, this is a warm-up. If I were to graph this, I would think, okay, the first things I think is, I know that the y-intercept is negative 8. It's this value right here. Because for the y-intercept, you plug in x equals 0. X equals 0 is, boom, that becomes 0, that becomes 0, and you're left with negative 8. Boom. So negative 8. Done. I know that this graph is actually going to be opening up downwards because of this negative. And not only that, it's going to be a little bit fatter than a regular parabola. Because regular parabolas, if it's a 1/2 in front, that basically shrinks it to be a little bit shorter. And when you take, remember that gummy bear thing I showed you? When you take a gummy bear and you shrink it shorter, it makes it fatter. So that's kind of what your parabola is going to look like. Then from this point right here, I can figure out exactly where the graph crosses the y-axis. Because what I do, or no, the x-axis. Because what I do is I set this equal to 0. This is y equal to 0. This is, f of x is a secret code for, for y. If I set y equal to 0, then I can either have this equal to 0 or this equal to 0, and that tells me that it crosses at 2 and 8. 1, 2, 3, 4, 5, 6, 7, 8. So it crosses here and here, so I know that my graph is going to look something like that. Are we cool? Does it mean, wait, okay, I can't see that from here, so I'm going to make the, by the way, is the question when it says graph, when it says we have to graph this, does it mean we have to fill in the graph? Because my computer won't let me graph anything. Yeah, well, I mean, that's why I make you do things on paper, because it's easy to draw outlines. But I'm very impressed with those of you guys who are, guys and girls, who type up all of your work. I think that that's way more work than I expect you to do. But I'm impressed. I mean, it's a worthy cause. Yeah, you would lose points if you don't do the graph, because the graph is kind of like, if you understand how to graph something, and this is the thing that I realized that Joy was learning when I was tutoring her, is if you know how to graph something, then you really understand how the graph works and how the equation works. I mean, that's kind of the whole point, is let's apply math. Let's not just like be able to do it. Cool? All right. Let me just see what it is I want to cover with you. I'm looking at exit pass. All right. I'll probably spend a half hour doing this, and that's going to run our class over by about 20 minutes, maybe. I don't think I'm going to spend that long. Here's my question. Are any of you guys in digital animation or 7th grade? No, you guys wouldn't be. Are you guys in AP US History? Yeah, Erica. If you check the thing on Desmos, I mean, technically that's cheating, but I don't see it as that bad of a thing. That's fine, because it's just checking your work. All right. Does anyone have to go any place by 10 o'clock? Okay. Then do you guys mind if I go to about 10 o'clock? Because I spent so much time in the beginning of class teaching you guys a little bit about something interesting. All right. Yeah, I'm sorry about the connection issues. I don't know how to fix that. I'm just going to come out and say it. I really feel like this this system that we're using is inferior to the system we used to use. All right. Anyway, let me kind of teach you guys something that I think that I started teaching. Erica. And Erica, do you mind if I go back and show you guys something that like what I was teaching you? All right, because I'm going to teach them the calculus thing, and I think it's really cool. All right, here, check it out. Ready? One of the things that we look at is, you guys are my 11th graders, aren't you? So you've had physical science before, and so you've been looking at like velocity time graphs, right? 10th graders, last year you had physical science. Can you imagine a velocity time graph? Okay. Where your velocity, like you could, let's pretend that you start at a stoplight, and this like dude comes and pulls up in a red Corvette, and you just be like, wait, isn't Barbie supposed to drive a red car? Like maybe this dude comes up and pulls up in a pink Corvette. He starts like revving his engine, like, yeah, and you're like, dude, are you like Barbie's husband or something? Or are you Ken who's driving this pink Corvette? I don't know. I mean, not to say that there's anything wrong with pink. I'm a big fan of pink, mind you, but I'm just saying. So you start racing this guy, right? And I drive and I'll be honest with you, I drive a super fast car. It is a Honda Odyssey 2006 minivan, which is not fast at all, and it just kind of makes me sound like a soccer dad. Which I kind of am, except the fact that my kids don't play soccer because they're not athletically talented, or they're not athletically gifted, which is fine because I'm not athletically gifted, as you can well tell. So, turns green light, we jump on the gas. I don't go immediately like that. That's not my car. Sorry. By the way, the pink Corvette will easily beat me, but okay, dude. You win, but you also drive a pink Corvette. So, there's that. But anyway, by the way, that's my phone. And I can't answer it right now because it's on the other side of the computer, on the other side of this glass wall. It's hard to get there. But you don't start going fast immediately. You start kind of going, or at least this is my car. I go slow like this, and I started increasing like that. In fact, if you could hear the squeak of the pen, it went, right? That's how it kind of sounded to me. But you can imagine that you go slower and you go faster and faster and faster and faster and faster. Are we cool with that? So if I wanted to figure out this, if I wanted to figure out the rate of change, because if I wanted to figure out how fast this thing changes. Actually, you know what? I'm not going to look at a velocity time graph. That's not what the graph looks like. I'm going to look at a distance time graph. I'm sorry. It's the measurement of x versus time. But if I wanted to figure out the speed at which I was moving at, I would figure out the slope of the line. Are we cool? But here's the thing. What is the slope of this curvy line? Because if I was going straight up at 100 miles per hour, it would be like this. Right? In 1 hour, I would go 100 miles. Let's pretend that's 100, and this is 1 hour. Okay? Something like that. So I can figure out the slope, and that's how the slope of this line, and that would tell me exactly how fast I was going. Here's the problem is, what is the slope of this curvy part? Because this is what real life is like. Your car doesn't immediately go from 0 to 100 miles per hour instantly. If it did, it would break your neck. Your neck would literally snap back, and you would die. So you would just kind of go 3, 2, 1, boom, and then you would just be dead, and then you wouldn't be going 100 miles per hour. So you know what? Even cars, they don't make rockets that do that. So anyway. You start off slow, you get a little faster. Here's my question that no one has answered yet. What is the slope of this curvy line? Alright, Here's the problem. There is no such thing. And this is probably why you guys are too scared to answer, which I'm fine with. But, you hang in there. Get some grit on you. The thing is, what you do is there is no such thing as a slope of a curvy line. It's a curvy line. I can figure out a slope of a diagonal line, sure, but it's got to be straight at least. So here's what we do. We say, all right, I can't ask you what the slope of this line, but what I can ask you is I can choose 2 points. Let's choose point A and choose point B. By the way, that T is supposed to be out here. That just means this axis is time. Are you guys confused as to what I'm doing yet? By the way, we'll make this f of x. Actually, you know what? Technically, it's f of t. Because the x-axis is t. All right. So now, I chose 2 points, and I say, okay, this is point A, and that goes up to there. This is point B, and that would go up to here. That would be like this translation from here to here. All right? Now, the corresponding y element to this A piece is right about here. Because if I were to get to that point, I would need to tell you to go this far out and this far up. Cool? And the corresponding y element to this B piece is right about here. Would it be all right with you if I call this f of A and f of B? This axis is the f of t line. But this is my f of A because this is A and this is, if I plug in A for t, I'll have f of A. And if I plug in B for t, I'll have f of B. Are we cool? Do you guys understand what I'm doing here? Am I doing something crazy? Yes? No? All right, let's use red. Now what I'm going to do is I can connect a line that goes through these 2 points. All right? And I can figure out the slope of these 2 points. Do you guys agree? All right. You forgot everything, but there's one thing I want you to remember about slope. What is slope? Starts with an R over R. The rate of change, rise over run. There we go, Lena. All right. So think about this. If I start at A and I want to travel along this red line to get to B, how far up did I have to go? If you guys want, I'll throw in some numbers, but that's just for now. I'm just going to throw in numbers just to make you feel comfortable, and then I'll take out the numbers. You guys ready? Let's pretend this is 2, this is 1, and then this is like, oh, Erica's already got it. If I'm talking about how high up I had to go, well, I ended here as far as height goes, and I started here, so wouldn't it be f of b minus f of a? Are you guys all right with that, or am I speaking crazy? Actually, that would be Erica. Erica, either you're speaking crazy or everyone's. All right, makes sense. All right, good. So the rise is f of b minus f of a. Cool? That's how far up I went. What's the run? B minus A. Exactly, because you end at B and you start at A. This, my friends, is this average rate of change formula that we've given you in the homework. It's f of b minus f of a all over b minus a. All I'm asking you to do is find the slope of a line that connects these 2 points. Because what you're figuring is the average rate of change, the slope, between 2 separate points. Are we cool with that? So that's where that equation comes from. So you can apply that to all of those different problems and the scenarios, and I hope that really helps you. that is actually what I'm asking you to do. That's where that comes from. It's not out of my butt and throw it up on the board saying memorize it. I hate memorizing this kind of stuff. I love memorizing the idea that slope is equal to rise over run. I'm totally fine with that. I can hang with that all day. But you tell me like blah, 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 blah. That's craziness. All right, fine, whatever. But I want you guys to understand that slope equals rise over run, and we're happy with that. Can I show you guys some calculus at this point? You guys are like, well, all right. Just hang in there, okay? This part won't be on your math test. This won't be seen in the ACT, but what I want you to do, all right, here's what I want you to do. I'm trying to develop in you fearless math people. I'm trying to become fearless. That's what I'm trying to do. This thing that we're going to do on Friday is called Grit Fest. We're trying to teach you to get in there and just do it. Well, calculus isn't as bad as people make it out. So many times people psych themselves out because they're taking calculus and they're taking physics and they hear that it's the worst class in the world, and it's not that bad. Let me show you the first thing that you're going to learn in calculus, and I think it's really interesting, it's really cool. Here's the thing. Say that we're traveling at this, along this curve. We're traveling, this is how the curve would look like for our travels. And I can give you the perfect scenario. I already gave it to you. You're in a Honda Odyssey, and you hit the gas. You're not going to go immediately. You're going to start slow, and you're going to speed up and speed up and speed up, and that's kind of why the distance between here gets bigger and bigger and bigger, faster and faster and faster. Can you guys envision this in your head? Now, we're driving, right? Pink Corvette over there. Go. All right. You look down at your speedometer. I think that's what it's called. Yeah, speedometer. What is that telling you? You know, it's a big dial in the middle of your dashboard. Is it telling you the time? Yeah, it tells you your speed. Does it tell you your average speed? What does it tell you? What speed is it telling you? Exactly what speed are we talking about? The speed at which you're traveling at that exact time, how fast you are going at that instant, at that exact moment. I agree with you 100%. Now, if it were a Japanese car, it would be in kilometers per second, but in this, kilometers per hour, but in America, we deal with miles per hour, and that's fine. I mean, that's neither here nor there, but really what I'm trying to say is it is telling you your speed at that exact moment. So that's almost like asking, what is my speed at B? What is my speed exactly at B? Now here's the problem. All right, let's go with A. What is my speed exactly at A? I'm going to use a different color. It might be hard to see. I'm just warning. What is my speed at A? Here's what you're doing. You want to figure out this speed right here. Can you guys see that? See this line right here? This blue line? We call that a tangent line. It's a line that touches this at one point. A tangent line to a curve is some kind of straight line. Here, let me go grab a ruler. We'll grab this transformer ruler right here. And it's a line that a straight line that kind of touches that parabola at one point. By the way, just to let you know, the acceleration graph, that's a parabola. That's why I teach you guys what parabolas are. But anyway, it touches at one point and only one point. Here's the problem that we're up against, though. All right? Let me explain to you the problem. You're asking me to tell you what the slope of a line is, but you're only giving me 1 point. How many points does it take to draw a line? Let me explain to you how stupid this question is. It takes 2 points exactly, because if I have 1 point, I can draw this line, I can draw this line, I can draw this line, this line. I don't know the slope is if you only told me 1 point? That doesn't make sense. So do you see the issue that we're up against? I want to figure out what the slope of this blue line is, but you only gave me 1 point. Well, here's what we can do. We got an idea. I know how to find the slope of a line that is connecting points A and B. I can do that for sure. You guys got it? Now watch what happens. Here's my point B. Now watch what happens if I start moving point B along this curve, and I move this point B closer to this thing. So my new point B is over here. What happened to this new ruler? Did it get closer or further away from this blue line that I'm looking for? It got closer. Now I'm going to move my point B even closer and closer and closer and closer and closer until the distance between point A and B is so small that it kind of blurs into 1 point. It's still 2 points, I guarantee you that. It's just I move them so close that they kind of seem like they're 1 point. What would happen to the ruler then? What would happen to the ruler then? Well, then it would be exactly the blue line. In fact, if I said, let's get this thing to be so small that it essentially goes to 0. I'm talking about the distance between B and A. Then I would say that this red line will match so closely to the blue line that I'll basically be able to say that they're the same thing. They are 2 separate points. They're just getting so close that it looks like it's 1 point. Are we cool with that? You guys happy with this idea? And it all comes from this. That's all it comes from. FB minus FA. This is how you calculate the slope of the red line. We don't know how to calculate the slope of the blue line unless we make B very, 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 very close to A. That means B minus A will be a very, 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 very small number. Like maybe B is going to be 1.00001 and A is going to be 1. So your difference, B minus A, is going to be 0.0001. In fact, let's even do it better. Let's go 1.0000000000001. And then A is still 1. So our difference is going to be pretty small. Does that make sense? In fact, a lot of times what we do is we designate this B minus A, we call it delta H. And delta just means the change in. Okay? And then we say, and then when I want to say that delta H gets really small, I'm going to write this. Limit as delta H goes to 0. So what I'm doing is I'm finding what happens when delta H, which is the difference between B and A, goes to 0. It gets really small, that distance between them. All right? We're cool with this? Is it a hard concept to understand? Okay, no. All right, let me show you something now. I'll be right there, 1 second. Let me just look. This will work. What do I got? I know this is backwards. Here, let me just fix the computer so that you can see it right side. Or the correct way. Hold on 1 second. Maybe eyeglasses. There we go. All of the writing that I did would be backwards, but now you can see this. What do I got? This is a calculus textbook. Okay? I'm going to look inside of it. chapter 2, chapter, here we go. Chapter 2. Let me just look real quick. Hold on. I'll show you what I'm doing. Just looking here. That's all chapter 2. Alright, now I'm going to go back to chapter 2. Okay, hold on. I got to find it. There we go. Okay, wait. Where is it? Oh, here. Alright, fine. I'll just use this one. I want you to look at a formula. Alright? Can you guys see that? It's blurry. What's about now? Can you see that? This is chapter 2, derivative of a function. F of x plus h minus f of x divided by h, and they are taking the limit as h goes to 0. See that LIM? All that comes from is this rate of change equation that we came up with. This guy right here, I know he's backwards. That's all it comes from. The rate of change equation. So I mean, what I'm trying to motivate for you is that what I'm teaching you isn't going to be irrelevant to your lives. Most of you will have to take calculus. I imagine that all of you would probably take calculus by the time you guys get to college. Because business majors use calculus. People who make money use calculus. Scientists use calculus. Engineers use calculus. So, I mean, this is what I'm teaching you. This is where this stuff comes from. Here's the motivation for learning this. Come on, you guys. When I usually teach this in a regular classroom, people are like, wow, that's so cool. But then again, I'm sure that you guys are saying that. You guys just aren't, writing anything down. Please respond to me because I like that interaction. Do you guys think this is cool? Or do you guys think, like, I knew that? That was like kindergarten. Dude. Well, good. I'm glad. I'm glad you think this is cool. I think it's cool. Like, seriously, if you pull open a calculus textbook and you look for that equation, it's called a derivative. That's the name we gave it. You'll find that that's exactly what you've learned in the past. It's not even that, like, complicated. It's going to look complicated. You're going to be scared, and it's going to look scary. But here's my point. Get some grit on you. No fear. This is what we do. This is how we do it in science. This is what physics is all about. Which is kind of my shameless plug that if you guys ever get the opportunity to, take physics. You don't need to take it from me. I mean, just take it in general. Take it in college. Take it sometime. And take the calculus-based physics. So that will really, really teach you a thing or two. Anyway, have fun. What I'll do is I'll take homework number 4 and I'll push it back to this week. So you'll have double homework for this week. I think tomorrow on Wednesday I'm going to start lecturing on chapter 6 stuff. But thank you so much for hanging out with me. I hope that today was enjoyable for you. It was definitely enjoyable for me. I felt like I did. You know what I mean? So how am I changing the what? The date? The calendar? I can't really read the bottom of that comment right there. How am I changing the homework dates? Yeah, you have function 6 homework due to as well this week. I'll tell you how I'm changing the homework. I'm going to push function 6 back 1 week. I'm going to push functions 4 back to this week. And then what I'm going to do is I'm going to do this. And this might open up the floodgates. But some of you don't have a good grade in my class. So what I'm going to do is I'm going to say, turn in any assignments you want this next week. It can be old assignments to help get your grade up. So I'm pushing functions 4. It was due last week. I'm pushing it to this week. Function 6, it's due this week. I'm pushing it to next week. We might have to double up on function 7 because I've already lectured on that stuff already. And I'm opening up the floodgates and saying, you can turn in anything you want, and I'll grade it. The deal is, if you do that, you have to email me and say, hey, Mr. Dalday, I turned this new thing in. Can you grade it? Because I don't go back and look through the old, I don't go back and look through the old drop boxes that I already finished grading and see if anyone turned anything new. What if you don't turn in work? Will it be marked down? What do you mean, don't turn in work? If you don't do the assignment? Oh yeah. If you don't turn in next week's work, you won't get the. I mean, you're talking about if you don't turn in next week's work this week. No, you turn in next week's work next week. But if you don't turn in an assignment and it was due, of course you're going to get marked down. Anyway, I hope that was understanding. That was an understanding move on my part. And I'll be honest with you, I think that what I'm going to do next week is, I might do this week, but I want to do it next week. I think I'm going to go over some ACT test with you. By the way, for those of you who didn't take it, it is really, really, really in your best interest to take the ACT test that I have posted up there. I'll let you turn that in late as well. I think I even gave you 4 shots to take it. And if there's only 4 options, A, B, C, and D, I mean, you really have no reason to get anything less than 100% on it. So, anyway, retake the ACT test. Take it until you can get as good of a grade as you possibly can. Because that is actually weighted much heavier than your homework assignments. So that one is more important that you take that than that. How's the ACT prep test graded? It's graded by the computer. I actually put in all the answers into the computer, and the computer graded it itself. Do you have to do function 6 today? No, like I said, I'm pushing that back to next week. All right, I'm stopping the archive. But for those of you who didn't show up for live class today, which is kind of a lot of you, you might want to definitely watch this last part. All right. Have a wonderful, wonderful day. Aloha.